Thank you all so much for, oops, now we're recording. Thank you all so much for joining us. And this is week 2, super excited. Week 1 was amazing. And thank you all for your hard work. You're gonna hear from the session leads today. Really all I wanna say is just welcome. And as you're thinking today, please remember, don't get hung up on the things that can't be done. We're thinking very far out. So acknowledge what can't be done, but don't get stuck. Define what you know about it, define what you don't, and move on to what you can discuss and what can be done. And Gary's gonna give us a little quick update for some of our lessons learned and what to think about, and then we'll get into the readouts.
Thanks, Nikki. So I just wanted to actually reinforce Nikki's point. I thought last week was great. I'm looking forward to this week and the next weeks. But during the sessions last week, there were some questions which came up about budget and funding. And I'm going to ask everybody not to think about that. Come up with bold ideas. Let's not worry about the funding. That's DOE's problem. And we are working behind the scenes to at least have the appropriators take this seriously. So I think at that point, I don't want to cut into the time. So I'm going to pass it back to Nikki and have her introduce the summaries.
Thanks so much. Yes, please go big, think really big. We are trying to change the world here. And remember, if you don't hear about something in your session or you need to get more information, we are not limited to only the session times. We can work outside of this. So I think you've all actually been introduced. So let's just go with the readouts first. So I think we have atmospheric modeling first. Ruby, are you ready to go?
Yes, can you hear me?
Yes.
All right, so I'm going to start sharing screen. Okay. Okay, so this is the atmospheric modeling session at a glance. Here is the list of chair and co-chairs of the session. Our session, we have 2 hours. We started with 2 plenary speakers, each speaking for 15 minutes. And then we followed by 4 panelists, each giving remarks for about 5 minutes. And then we even have time to do 2 breakout sessions. We have roughly about 90 invited participants. 28 white papers were binned into our session, and most of them are summarized in quad charts if anyone interested in having just a very quick look at these white papers. So a little bit more information about the breakout groups. As I mentioned, we were able to do 2 rounds of breakout sessions. We break down into several different topics listed over here. Our plenary speakers, panelists, as well as the co-chairs all help to moderate and take notes during the breakout discussion. So the breakout groups, they were charged to address the 5 overarching questions that were given to all of us. But given the time that we have for reporting back, I'm just only going to briefly summarize some of the points that were made regarding what are the grand challenges, what is the state of the science, and also our near-term and the mid to longer-term goals. So starting with the grand challenges, so these are some of the points that were made during the breakout discussion. So accurately capturing atmospheric physics, and there are many atmospheric physics, right? So many processes that produce precipitation, boundary layer, aerosol cloud interactions, etc. Training the model to be optimally skillful on multiple time scale. I think the key is really multiple time scales, because there are many different time scales that we wanted to be able to predict. Create differentiable global models with smooth relationships between inputs and outputs, which is really important because that would provide us a better tool to do sensitivity analysis, physical interpretation, as well as data assimilation. Addressing the knowledge transfer across scales, as well as addressing the lack of training data. Combining AI machine learning or using AI machine learning for data assimilation to help improve initial and boundary conditions. Transform the objective calibration of model parameters so that we can use the model and calibrate them systematically at multiple resolution. And then creating a seamless data and machine learning model management system. Seamlessly predicting extreme events across scales, and then applying AI machine learning to discover unknown relationships, as well as quantify extreme events. and use AI machine learning to gauge the representativeness of observation, but also allow us to incorporate observations from the distant past, not only in the last decade or so. And then enhancing UQ in all aspects, including modeling, observation, and data fusion. And then lastly, improving physical understanding and interpretability, as well as building trustworthiness of AI for weather and climate. So these are the grand challenges that we felt important. So here is a summary of the state of science. Our plenary speakers both have talked about models that are able to be trained using machine learning. For example, there are already now 2 sources of training data sets for machine learning that are quite useful. One is using global storm resolving models at 2 to 5 kilometer resolution, but also highly accurate global reanalysis at pretty high resolution between 25 to 50 kilometer. So some of these studies definitely show promises that machine learning can be used to train coarse grid atmospheric model to behave like fine grid convection resolving models. But if we are really going to use these type of models for operation or for climate modeling, we need to really consider real geography. And for that part, currently machine learning enhanced AGCMs are still a work in progress because sometimes they would encounter model crashes. There are also some issues with poor generalizability to climate, for example, in the future where it may not be representative by what we have observed. And also there could be mean state drift. And then a number of state-of-the-art approaches have been in current use, but blending Bayesian and data assimilation method is still underutilized. We have been able to use discrepancies across multiple independent data sets to derive uncertainty of observation, but such uncertainty still propagates to the machine learning model. And then there are many different uses of AI machine learning being explored. For example, replacing parameterization, using it to improve forecasts, classify regimes, evaluate model, discover new knowledge, etc. And then there are also many technologies being investigated to tackle grand challenges like digital twin, model catalogs, adversarial models, and many different uses. So that's the state of the science. And I'll quickly go into the last 2 points about near-term, less than 5 years activities, as well as some of the activities that could be done in 5 to 10 years. So for the near term, if we are looking at global modeling, whether it is just atmospheric GCM or couple modeling, there are several points that were made. We can design user-friendly machine learning system and workflow on DOE computing resources. Train the model using the 2 reference data sets that we mentioned before, the cloud resolving simulations such as produced by the DOE E3SM cloud resolving model, or high resolution reanalysis data. And then interactively couple the model into a full climate model to really begin to explore this type of method for fully coupled system, and experiment with different machine learning architectures and training methodologies to optimize the system. Regarding parameterization and observation, we need to prioritize what are the physical processes that need to be addressed by this type of method, building machine learning emulators, ensuring that the ML parameterization are physically consistent, better understanding the domain of the training data sets, and identifying observational deficiencies. And then the traditional models are still very much very useful in the next 5 years. And so calibrating those models are important, particularly using machine learning type of method. So 2 suggestions were made in standardizing the cost function for model calibration, and then developing a publicly available perturbed physics ensemble training data sets that can be used to improve calibration of traditional models. And then lastly, ML AI type of application and approaches, jointly developing standards for and a searchable catalog of AI relevant data sets, develop a service for sharing AI models, searchable by problems, and then develop lessons learned track in journals. We find that oftentimes people have tried different methods, some fail, some are successful, but the failed one often are not reported. So that could be very helpful. And then lastly, in 5 to 10 years in couple modeling or AGCM, work with application community to adapt the prototype that are developed in the near term to suit their particular needs, and then work with the IPCC GCM community to cross-fertilize ML best practices. In parameterization and observation, strive for physical understanding and interpretability, develop more sophisticated uncertainty estimate, focus on scale-aware parameterization, extend limited space-time observation to different time periods and spatial scales, incorporate observational uncertainty to avoid overconfidence, make emulator operational in weather and seasonal forecasting model. And then lastly, there are also a lot of suggestions for AI machine learning application and approaches, including developing and applying multi-physical and multi-scale method, co-design for physical modeling, measurement, as well as theoretical development. Enable data and model surface to be used extensively by the community, provide greater availability and documentation of the models, make data and from the model and observational data available as they are produced. So I think a lot of it is really making the process more seamless and making the methodology and the data available. So running AI model automatically on data as it is being produced, and then making AI models widely accepted, trusted, and in use. So with that, I'll stop sharing and see if there might be any questions for.
I don't think we actually have time for questions for this, but thank you. That is actually a very good rundown, and I do have a lot of questions. And for those of you also do, we will work to get those to Ruby and the crew. And that was great. Thank you very much.
Thank you.
Let's move to land modeling. And Beth, do you want to jump on?
Yes, I can share my screen.
Okay, I can see it.
Does that show?
All right.
Okay.
Now, yep.
Can you see it?
It's kind of
Okay.
reloading. I can see part of it. Can anyone see all of it? Is that me or?
It's not just you, Nikki. I can only see half.
Maybe, yeah, I could see it in your slide form
Okay.
before it's presented. So maybe just
All right, I'll do that.
make it as big as you can in that and go. Oh, I can see now. It
That
looks
looks great.
Oh, you can see it now? Okay, good.
Yeah.
So I'm just going to give you a quick summary of the land session. We started off with a couple of plenary talks, followed by 1-minute flash talks by all of the white paper authors. And then that set the stage for our breakouts. We had 5 different breakouts across different themes in the domain science. So disturbance, photosynthesis, physiology, land atmosphere, below ground, and land use and land cover CRAPS. So I pulled out some of the themes from each of these breakout sessions to kind of match with the 5 different questions that we were addressing. So the grand challenges that were identified by pretty much all of the groups were uncertainty quantification, and not just in the data, but also in the models as well. Scaling, this is an issue that's going to come up, I think, in all science domains, but we have all of these point scale data or small, site data observations, and how do we scale that up to the globe, including accounting for, and recognizing hot spots and hot moments, land use change, subgrid parameterization, looking at long-term versus short-term fluxes. We tend to do really well in the short term with models, but maybe not necessarily for the long term. So how do we improve models for that? And data was another really big issue. We have a lot of data, but we don't really understand it because it's not all in one, concise area. So we don't know exactly how much data we have, and what are some of the unknown pieces that we should be looking at. Using the historical data that might be more difficult to process, and bridging gaps in our spatial and temporal scales, especially when we have sparse and scarce data. Using long-term observations and extending current observations so that we do have more of these long-term observations, and just looking at the other data sets that we have and trying to get the most bang for our buck. including extreme scale observations, which are problematic. We don't have that many. And then looking at, how we can expand those data sets to gain more knowledge from them. And some of this could consist of data mining or the creation of kind of a large harmonized database. One of the issues that we need to address is terminology and being consistent across different groups, and how we collect that data. There's data collected at different frequencies, spatial, temporal, and how do we harmonize and unify all of that. Capturing heterogeneity is another really big issue. And so the example I have here is with urbanization, but it also goes to soils and plants as well. And then using emulators and building hybrid models. And those are going to be important, as we get to these more computationally expensive processes that we're trying to include. How do we build those directly into Earth system models so that we can apply those methods across a wide range of ecosystems? And then finally, how do we explain what's going on in our AI instead of having this black box? We want to understand, what's going on. And in some ways, we can integrate the biophysical rules and our own understanding of the domain science. But also, what can we glean from the AI that we don't know going into it? So the state of the science, there's been a lot done looking at parameter uncertainty and sensitivity. We've used some ML along with our domain knowledge of the physics to partition fluxes, to map plant traits, to start to benchmark models, and maybe look at imagery classification. But we need a standard to annotate the data, harmonize it, and then identify those classifications so that they're consistent. And that's, again, back to that terminology. How do we mine the data, especially data that's, we have a ton of data and we can go through it, but it's a matter of looking at, making sure that the terminology is consistent across and understanding, what we can use that, especially in biogeochemistry, which hasn't been done as much. And there's a lot of other data that we could use that we haven't quite taken advantage of. So we have this digital trace data of humans. We have low-cost sensors and potentially robots that can be used to collect data in maybe hard to reach areas. There's satellite information. And then developing transferable AI that we can share across different ESMs. So there's a lot of opportunities. Again, the scaling is a really big issue. How do we go from these small scale observations to global scale? And data is again, a really big issue. Harmonizing the data that we have, standardizing it, creating labels and classifications, understanding the data that we have, and getting down to identifying the data that we need. Creating a center might really help with that. We could develop a model data integration or an assimilation network. We could use it to process data that's too intensive to process. We could use machine learning techniques for that. And we can even pull in some non-traditional data, such as like citizen science that could be used, or it could be used as proxy for other data that we can't collect or we don't have a long enough time series for. There's a lot of remote sensing data that we could possibly use to train the artificial intelligence and we can use that to build that heterogeneity into the models, substituting space for time, especially when we don't have these long time series of data that we need. And then also classify extreme events, and especially the rare ones for predictability. Including the data model integration, we recognize the importance of the quality and quantity of data that's collected, and so we need more data. And this can all be used in models to reduce model bias, parameter uncertainty. We can start to develop hybrid and surrogate models, and those could be useful to replace processes that are really expensive computationally or have a lot of uncertainty, or we just don't understand them that well. Also developing synthetic data sets so that we can use as test cases for AI and ML techniques, especially when we understand what we put into those data. That would be, I think, useful. And then once we start to hone in on some of these ML techniques, we can use those on our observations to start to capture emergent behavior in ecosystems and capture those outlier events. And I think that's another really big issue, is trying to capture these extreme events that they're somewhat rare and more outliers and not generally included. And then from that, we can start to understand, this knowledge-informed AI, which is going to be really important in the land. So the research priorities is education. We don't understand the full potential of AI. So diving a little bit deeper into the understanding, getting those communications across between, the domain scientists and the AI and mathematicians, I think is going to be really important. And once we start to do that and we start to understand the full potential, we could use that to understand processes a little bit better and start to derive those mathematical models for Earth system models. And those can be used for either fine scale models or this, physics-based hybrid surrogate modeling. And we can start to extrapolate, outside of our training space. And this is starting to capture some of those extreme events. And then also understanding when we should be using machine learning and when we might want to use a mechanistic model. What are the benefits and disadvantages of each of those, and how to decide which one is the best. And finally, applying sparse data so that we can inform our global models, I think is going to be another big priority. So just to kind of highlight a few goals that are from the different sessions, short term is really looking at partnerships, bringing in more students and postdocs and training them in machine learning and the domain science, getting in data flowing between the public and private area, and then furthering our understanding of what's really possible with machine learning so that we can develop a roadmap for the future. In the long term, or in the midterm, we should have more confidence as we start to apply these techniques over a range of processes. It could help us reduce uncertainty in models and also in the data sets. And will also help us identify gaps in our knowledge that can inform our observations and even modeling designs. We can start to explore some hybrid, maybe surrogate models, and develop some of these transferable AI methods that can cross between the different Earth system models. And then finally have AI ready data that we can use moving forward for more machine learning. And in the long term, developing an institute or some infrastructure that can support this community effort that we'll be building on the previous lessons and experiences. And by then, we expect that we'll have some very successful techniques developed that will address the scaling issue, building emulators, understanding some processes that we didn't before, which will help us to generate new hypotheses. And that's all I have.
Great, thank you, Beth. That was wonderful too. There's a question in QA, if you don't mind answering it offline. Sure. And then we'll have Giri give the update for the data acquisition.
Okay, let me share my screen here. Are you able to see my screen?
We can see it.
Okay, thank you. Good morning and good afternoon. I'm going to summarize the key actionable items from the data acquisition to distribution breakout session. Okay. So very briefly, so we talked about the full data lifecycle and what are the primarily two opportunities. One for how do we improve the data lifecycle components using AI, and then the second one is enabling new capabilities to support AI and ML use cases. And within that, we talked about all the standards and protocols from collection to distributing the data, and what are the key items that we want to think about in terms of data discovery and cross-domain ontologies when it comes to AI-based research. And so with that long list of topic areas, we actually had three breakout subtopical breakout areas. The very first one is AI informed data collection and edge computing breakout. And here, the grand challenges and gaps includes like representative sampling in environments with high spatial and temporal gradients is always a challenge. And how do we collect like improved data conditioning and perform QA and QZ that will meet the AI use cases. And so currently the observing systems designs are suboptimal primarily for AI, ML for like immediate feedbacks and so on. So how do we improve our data collection activities? So with that, we discussed about short-term and long-term goals. And the first one is like explore optimal experimental designs and strategies, and with the use of potential test beds, including the DOE arms, the mobile facility 3, Southeast US use cases, where Shanghai provided few specific use cases. And so in terms of edge computing, we want to look beyond 5G networks, such as neuromorphic computing and quantum computing sensors, and so on. And also we talked about adaptive agile data collections using drones, UAVs, new sensors, and new satellite-based collections. And we very briefly talked about current test beds, including the arms sale campaign, as well as the Southeast US and other campaigns where we can potentially use satellite communications like Starlink, where we can have like enable edge computing where the data is collected. So, okay. The second topic, breakout topic, is developing and training data test data sets for AI and ML use cases. And here the challenges include like data acquisition guided by physical-based models and prior knowledge is a challenge. And quantifying and controlling the propagation of error in training data sets to the models is also a challenge, or the gap that we observe currently. And for the data submitters, we thought like an AI automated QZ framework could provide instant feedback, and no such thing is available right now. And utilizing data sets guided by data value such as diversity, cost, deployability, all those things yeah, it's complexity for the data collection and utilization. And there's no online AI ML driven optimization in models that the group could identify. That's something that we want to look into that. And challenges with the data integration from data collection from platforms, scales, and accuracy is an existing challenge. And if you don't address it, we'll get into this AI activity as well. And the overall technical challenges associated with our cyber infrastructure, both software and hardware side, is a challenge. And so in terms of software and short-term and long-term goals, we feel the need for developing AI-guided symbiotic framework for integrating models and observations, and developing AI-guided data acquisition and data trustworthiness is another topic we want to get into, and bridging the scale resolution gap between models and data using AI that could be developed, and building emulators of complex processes such as the E3SM would be key, and supporting cloud computing platforms for both data analysis and also data distribution is something that the group discussed. Okay. All right, so the last breakout that we had is on data lifecycle ontology standards and protocols. Here, the primary challenges are lack of AI expertise to support goals. Talking about the human resources, these are the very highly sought talents by various industries, and recruiting and retaining them is always a challenge. And data volume and diversity makes much harder for AIs to consume the vast amount of variety of data that we have even within the BER landscape. So lack of cross-domain ontologies, standards, and protocols makes the data usage harder for AI use cases. So existing data lifecycle methods are, as it stands, are currently inadequate, especially with the MODEX, which requires integrated model and data artifacts with immediate feedback from one another. It's something that we want to improve. And there are challenges with the AI approaches for data accuracy and reproducibility, and a lack of full data uncertainty characterization, such as the error propagation, makes this further harder. So what are our short-term and long-term goals? So we propose to explore AI data reduction and synthesis capabilities to address the multi-scale questions. And here we discussed about leveraging upcoming test beds such as the Southeast US and the SAIL campaigns. And also there is a need to create working groups and train our current domain and field scientists, computational scientists focused on AI use cases. So we talked about reducing the barriers for BER to work with Asker to develop the tools we need for increased use of AI. So in here, one suggestion was BER community needs to better articulate tool requirements that would facilitate more rapid data analysis. So a new idea was proposed to use the AI techniques for developing and refining cross-domain ontologies, which is key for our complex use cases like water cycle and hydrology. So finally, we want to have an actionable cross-collaboration on development of data standards, protocols, and ontologies within BER and also broader community. Thank you.
Thank you, Giri. Great. Those were wonderful readouts, and you guys, you did that so fast. I'm really grateful you put all that information in there. We're seeing some clear trends already. I think everybody, let's take the break, and we will come back at I believe, is it 15 till or 20 till? 1 second here, get it right. 15 till, and we'll start our first session for the day. So feel free to break. Session chairs that gave readouts, if you'll hang on 1 second, I just have a couple of requests. But thank you all, and we'll see you in the session. So if you guys can either, would you mind going into the agenda that's on the Google Doc and linking your slides from there? That would be the easiest for us to find where they are.
Okay.
That'd be great. And then we will we'll get those linked in the web when we do an update on that. But this way, at least the participants that can see that agenda can use that. And we've been sending that to a lot of people. So I think that would be the quickest way for people to see your readouts and catch up if they missed it. But great start. Thank you all very much. And
I gotta say, this is the first. I was just gonna say, this is the first test case of report outs, and they were great.
You guys did awesome. I'm a little shy that we don't have quite 10 minutes for the others, because I think that was still super fast, but it was just enough for you to get the information in. So I think we might have to adjust or get into our break a little bit, maybe shorten it. I don't know. We'll see what we can do on next week. But thank you guys for fitting that in. That was a lot to do. All right, enjoy your break, and we'll see you on in a minute.
All right.